for each of these series of data, I guess, from the different jumps. You can see for our jump squats we did one with 0 kilos and all the way up through 20 at 10 kilo intervals up to 90 kilograms. And for each one we've got a column of time data and a column of force data. I'll just zoom in a bit so it's a bit easier to see if you're watching this on a small screen. So we've got time and we've got force. First thing I'll do is just plot a force graph just so you can see an example of what this looks like. So fairly similar to our counter movement jump. Obviously this is a jump squat with no load, so essentially the same activity. I'll just clear this graph up a bit so it's easier to see. So we've got the same sort of curve, the decrease in force, the increase, and then our takeoff and landing during our flight time here, and then our peak landing forces as well. And what we're going to do is from this graph calculate our impulse, our velocity, our displacement and our power values. The first thing that we need to do, as I mentioned in terms of calculating impulse, is to subtract our body weight from these vertical data, because we said if we have forces equal to body weight we're not moving, so our impulses relate to how much force is generated above or below our body weight value. And the best way to do this, as we made sure the athlete was standing still for at least the first second of every trial, is to calculate the average of the first 1,000 force data samples. So the average from B2 to B1001, because this is sampling at 1000 Hertz, 1000 frames equals 1 second, so averaging these 1000 values will give you hopefully an accurate estimate of our weight in newtons. The next thing to do then is to calculate what we call net force, and this is simply the force measured by our force platform minus the person's body weight. So whether the net force was positive or negative, whether force was above or below our value for body weight. And what we can do is copy this down for every frame, but obviously you have to be a little bit careful when doing this, because if you just copy it down, you'll see as we go down each column we've got inaccurate values, because if you look on the right hand side it subtracts the one below it each time. So for example in this cell we get the one below weight, in the next cell the one below that. So what we want to do obviously is fix it so it always subtracts the weight cell. Now the way to do this, if you go back into your calculation in cell C2, add a $sign before the number, and then if you copy that one down, you'll see now it's always subtracted the weight value. So if we click in any one of these cells, you can see it's B11, so our force at that time, minus I1, our weight value. So don't forget to put that $sign in to hold that weight value throughout the whole column. Now that we've got our net force, the next thing we can calculate is impulse. And the first thing we know is we need to get an impulse value for each point in time. Our first impulse at our first point in time is 0, and then we can use our trapezium method that I talked you through in the PowerPoint slides to calculate impulse at each data point in time now. So the way to do this, we said it's half times the two force values, so the sort of the, I guess, giving us the average of the two sides of our trapezium, multiplied by the base, and this will give us an impulse value for each single frame. So what we then want to do is keep adding up one after the other, and this will give us a cumulative impulse that then we can take at any point to find out the total impulse generated up to that point in time. So the kind of formula we need to use to calculate our impulse, well, firstly what we want to do is identify our two force values, the height of our two sides. So if we take C2 and C3, and we want the average of these two, so dividing it by 2 or timesing it by a half as I showed in the initial slide, and then we need to times this, which is the star in Excel above the 8, by the time interval, the base of our trapezium, which is always going to be 0.01 seconds. That's our time interval between each of our frames. So if we close those brackets, again make sure you've got your brackets in the right place so that you're adding, dividing and multiplying the correct things, and then this formula as it stands would give us impulse for just this one frame in time. And what we want to do is keep adding on all of the impulses in each consecutive frame. So if we add on the one above and hit enter, we can then copy it all the way down the column, and each time it calculates a new impulse and adds that to the previous cumulative value from the cell above. So you can see as I go down, just in the bar at the top here, it keeps adding on one more each time. So this gives us a cumulative impulse throughout the entire jump. The next thing hopefully you'll remember is from impulse and the impulse momentum relationship we can calculate values for velocity. And to do this we basically need to divide our impulse values by our subject's mass. So the next thing we need to calculate is the mass of our subject, and this is equal to our weight divided by gravity. Again, hopefully something that should be familiar to you, and we did go through in one of the earlier lectures as well. Now the way to calculate velocity, as we said, is simply impulse divided by mass. But again, don't forget to put the dollar sign in front of the mass value or in front of the number 2, because this will then hold that cell when we copy it down the column, so we're always dividing by mass, not by all of the cells underneath our mass value. So if we enter that one in, copy it down, just check that it's always done divided by mass, which it has. It's always done, if we look at any cell, divided by I2 mass. We've got our velocity. One other thing we can look at is displacement before we move on to power. So in our displacement column here we have an initial displacement, we have to put that in of 0. We know our initial velocity was 0, so we don't need to correct this. If for example we knew from video analysis that say this were a drop jump and we knew they had a downwards velocity of -1 meters per second at landing, in this first cell you could take -1 from your value and then it would correct this, because all these data at the moment is a change in velocity, which is fine because we know velocity started from 0, but if you did know an initial velocity you could correct this column accordingly. Now if we think about displacement, we said displacement is equal to velocity times time multiplied by, velocity times time, and then keep adding them up one by one, because that will give us a displacement for how much someone's moved by in each frame. So equals velocity times time. Again, make sure you put in the time as 0.001 because it's our time interval, not the actual time value. And what we need to do, again, if you put this in brackets to make sure that this part of the equation stays always E3 times 0.01, is then add on displacement from the previous frame. So a bit like we did with the impulses, we're adding up displacements from each consecutive cell to get an overall displacement, because these displacements are just how much he moved in each frame of time. And what we want obviously is how much has he moved relative to his initial start position. So again, if we copy that down, we can get a whole column of displacement data. The final one to calculate, and I guess the most important output for your coursework, is power. Now we said power is the product of absolute force and absolute velocity. So in terms of our data set here, absolute force, column B, times absolute velocity, column E, gives us some values for power. And if we copy that down, you can see at the start we're standing still, so very small powers. What I'm going to do now is just plot a few of the graphs so you can see the actual sort of data that we've got, and then I'll just explain about determining peak power. So we've plotted the time and force graph. If we plot the velocity graph, you can see, again I'll just clear it up so it's a bit easier to see, standing still for quite a while at the start, then velocity goes negative as they squat down, positive as they then come back out of the bottom of the squat in towards takeoff, and then after takeoff their velocity decreases linearly here because of gravity. So this acceleration during this point is the acceleration due to gravity, and then they land, break their downwards motion and come back to pretty much standing still. If we take a look at the displacement data, hopefully again this should make sense. If we look through it, they stand still, start to squat down, and then come out of their squat, reach a peak jump height, and come back down during landing. And you can see it was a bit of a wobbly landing on this one, and they actually stepped off the force plate, so displacement never came back to just standing still. Obviously what we're interested in is everything that happened up to takeoff, really, if we're looking at peak power, so this isn't an issue for this case. Finally, moving on to the power curve, if I just plot this one as well. Okay, so you can see from our power data, just try and clear the grid lines. Again, if we think just up to takeoff, so our takeoff was at around 3.5 seconds, this phase here is during the air, we get negative power as they squat down, positive power during the concentric phase, and a large negative power upon landing. And what we're interested in is what's our peak positive power value during that concentric phase. So you can see from the graph, I mean quite hard to see on this scale, but it's probably somewhere between 5,000 and 6,000 watts. Obviously the way to determine that in Excel is to use the equals max command. So we've got here equals max, and you can then select whichever cells you want it to look through. So in this case we want it to look through column G, so we're going to go from G2, and there were 6,000 cells of data at 6 seconds long. So throughout the whole data set for power, our peak power value was 5,482 watts. So at a load of 0 kilograms, peak power was 5,482 watts. And hopefully this procedure will become a lot quicker as you now do it for the other trials. You can go through, look at the jump squats with different loads and calculate peak powers for those as well. Obviously, for example, there's other things you could look at, such as jump height. And again, if you were interested in this, all you're looking for is the maximum value in our displacement column. So again, throughout the whole data set, peak jump height was 0.504 meters, 50.4 centimeters. And again, you could check that on your graph to see that it looks roughly correct and that it's occurring at the right point in time. Also, you could look down the force data, identify the point of takeoff, and look for how much impulse had been generated by takeoff, and also what the velocity was at takeoff as well. Other variables that you might consider to be interesting, but as I said, the main point of this part of your coursework is basically just to calculate these peak power values for each of the different weights that we've got for our jump squats, and then to calculate just a power load curve to see how power changed with different loads applied to our jumper.